Hello and welcome back to Calculus 3. We are going to discuss integration in cylindrical and spherical coordinates. We haven't done anything in these coordinates yet, so let's first learn about the coordinate system and then learn how to integrate in those systems. First off, we have the notion of polar coordinates and rectangular coordinates, and we know that polar coordinates and rectangular coordinates complement each other. They are not in opposition. They do not compete which one is better, which one is worse. Simply, each one is useful in its own domain. You do not want to work with any kind of edgy, sharp objects in polar coordinates, and you are trying to avoid using rectangular coordinates when the objects are rounded, because polar coordinates work the best in the kind of circular environment, where the rectangular coordinates work well with squares, rectangles, and triangles. So we are going to have the same situation now. When we move from 2D into 3D, we have our XYZ coordinate system, which will be known as rectangular, and then we have cylindrical and spherical coordinates, which would deal with roundness. Now, I'm going to say over here that for the 2D, we have XY world, which is boxy, and then we have our theta world, which is rounded. So in a nutshell, that's what we have. Now, what we are going to do is we are going to go now into 3D, and we are going to say I still have XYZ, which is the boxy world, and that's going to look like this. It includes pyramids and all of the shapes that that we dealt with in a previous lecture. And now we have two new systems. There is a system of cylindrical coordinates, which is r theta z, which has cylinders as the base. Now note the r theta input for that one. And then we also have a spherical realm, which is going to be rho phi theta, which is dealing with ball, right? The sphere. So these are the new ones, the red and the blue. Now, this over here is new way to portray. I have no clue why we have to use a rho all of a sudden if we used r in the previous, right? But I need you to see the r theta polar coordinates base again. So what we have here is two coordinate systems now in 3D that have polar coordinates as the base, and then we have either straight up upgrade, which is, as you can see, a straight walls up for our z for the cylindrical coordinates, or a rounded angle, right, which gives us ability to curve in the polar in a third dimension, which gives us spherical. So cylindrical coordinates are first. So for cylindrical coordinates, we have what? For cylindrical coordinates, we have a cylinder. That cylinder has on the bottom, it has the radius r, the theta all around, because maybe you want a half of the cylinder, which is 0 to pi, or you want the entire cylinder, 0 to 2 pi, or maybe you want a quarter of a cylinder, right? 0 to pi over 4. So we know how the polar coordinates work. So that's our base, and then we have a straight up z, which is the height. So cylindrical coordinates will be just your polar coordinates, and then you just add z to it. So nothing different. All of the conversions between the polar and rectangular are the same in this case. So you have the xy z convert into r theta z by using the standard conversions, where r is equal to square root of x squared plus y squared. Theta is the inverse tangent of y over x, and z equals z. So just the standard polar conversion, and then z equals z, which is not conversion, just copy it. Now, there's not that much that we need to look and learn about, cylindrical coordinates. You find the point in the plane, xy plane, using polar coordinates. You draw out the radius and you swing it for your angle theta, and then you just bring it up z or bring it down z, whatever the value is. That's simple. What we want to focus on here, obviously, is integration in this realm. So we are going to take a look at, first we are going to set up the integral. Now, guys, this is just a straight up upgrade to your polar integration. So whatever the double integral was, you Control C, Control V, right? And then you just put the z integral inside of it, right? So that will allow you to have a pipe with some kind of wavy z on top and a wavy z on the bottom, but because it's a 3D integral, right, you can also have something in the integration, so you can talk about fourth dimension, whatever quality you want to discuss of that object. So what is the integral for this? It's very long to write, so I don't know if you want to wait for me to write it out or whatever. So we are dealing with the triple integral over region D of x, y, z dv. So it's a 4-dimension, right? You have a dv times f, that's a 4D. And this is equal to integral alpha, beta, then we have another integral and another integral, and then we have f of r cosine theta, r sine theta, and then z. And we have dz, r, dr, d theta. There we go. And I have to do the limits here. So we have g of theta and h of theta. And then we have a capital G of r cosine theta, r sine theta, and h of r cosine theta, r sine theta. This is something that you should leave on napkin as you are leaving the restaurant, because for you this will be nothing to remember, like zero effort. But if someone sees this written down, they immediately think that you are up to no good. All the time. I left one of these in Disney. Yes. Easy, like that. 5 years old, of course, it's already. It just started fun. Yeah. No. My son's playing Minecraft like 12 hours a day. And I'm tapping on the shoulder. I hope that's all he does for the rest of his life. Nothing else, yeah. It's like, okay, money gives you happiness. Really? Great. You know, people who play Minecraft online, they make like 300,000. It's like, great. So yeah, there you go. Either that or a plumber. I mean, that's definite. I don't put a penny for that education. No, none. Here's a professor who doesn't want his kids to go to college. But no. Trade, all right? Plumber or electrician, right? You will be buying a hotel in like 6 weeks. No, I'm serious. I used to work at this restaurant, and owners were trying to sell it for $1.6 million because it also had the apartments above the restaurant. $1.6 million for 3 years. And then they dropped the price to $1.5 million. A contractor comes around and pays cash for it. And like, yeah, here's the here's cash for you. They just, you know, go away and retire forever. And you have no idea how much. I mean, if you want to go update the kitchen, you have to, yeah, 26K, you know, just put up a packet and paint the wall, that's it. 26K, and then you have people that work for that for a whole year. That means you don't get to live in any form. Like one kitchen remodel for like a weekend. Bathrooms, like 15K, and really? Done. All right. So let's talk about this, guys. What is this r cosine theta, r sine theta? Well, it's just a fancy way to write x and a y. So, right? Is that the way to write x and a y in polar coordinates? Yeah, all of a sudden this equation is a joke, right? What do I have? I have theta at the ends, right? The theta at the end is alpha and beta limits. I have the dr, well, this, the middle one, g theta and h theta, that's the same as the 13.3 polar integral, right, for non-rectangular, when you have a circle in a flower or flower in a cardioid or whatever, right, so you put those guys there. And then what do you have here? You have, well, let's go in the middle. So function f is x, y, and z. Yeah, it's x, y, and z, you see that there, right? But you have to express that in a polar form. So your x is r cosine theta, and this is r sine theta. You learned that in Calc 2, so that's not new. And then you have capital G of x and a y, and capital H of x and a y. So, as I said, this formula is a joke, right? Which is why you should just quickly write this on a napkin, just leave it behind, casually leave the... There should be a t-shirt with the formula like this. It's just a joke. Or which part of this don't you get? It's like polar coordinates, some of the, you know. Anyway. So what do we have? Let's go and take a look at the problem. Let's integrate. How about we integrate half of the cylinder? There we go. That's y. That's x. That's z. Say that this is the elevation of 1, 2, 3, 5, and the radius is 2, and that's all we have. So how do you find the volume of this? Well, should I say obviously, you will just say, oh, it's half of the cylinder. So the volume is 1/2 base times the height, which is 1/2 pi r squared times the height, which is 10 pi. And you are done. That's what it is. But then the person you were explaining this to said why, at which point you go, okay, here's why. Triple integration, because this was not clear. We go with polar coordinates. I have my domain. You know, just bear with me, right? I have my domain as half of the circle with the radius 2. Equation for the circle in polar coordinates is r equals to 2, but my theta is going to be cut from 0 to pi because I only want the upper half of the circle starting at 0, ending at pi, because I only work with half of this thing, right? So now what I have is I described my domain. So now I have a volume of this thing to be the triple integral. I'm not putting anything in here. So I only have the z r d theta, right? Theta is 0 to pi because I only want half of the circle in a base. Radius r goes from 0 to 2 because there is no hole, there's no second semicircle or anything inscribed in terms of flowers or whatever, so it's just 0 and 2. And then z, two flat planes. There is a plane at 0, which is the floor on which this object rests, and the elevation 5, straight flat thing on the top. So there is the integral, and the answer for this is 10 pi. Now, you know, skeptics will say, well, 10 pi, that's a government conspiracy, so let's actually show that's not true. So when you integrate out z and you put limits, right, you will get z, and then you will have 0 to 5, so it's 5. Now you integrate out 5r, you get 5 halves r squared from 0 to 2. Still have d theta. Why am I solving this? This is 0 to pi. You plug in 4 times, cancel 2, so we get 10 d theta, which is 10 theta from 0 to pi, and there's your 10 pi, and you move on with your life. So we just did a whole bunch of work to show that our arithmetic, our algebra formula from 2,000 years ago actually works, right? Clearly, this was not something very difficult to do because the top and the bottom of this particular shape were flat surfaces. There were z equals 0 and z equals 5. So that didn't bring any spice to our problem. Also, we did not have any function inside the problem, so that also didn't make integration worse in any way. So technically, you are looking at the cheapest possible problem that you can run into as you are solving these things. But then remember that we can have a lot of fun with these shapes. We had so much trouble solving the volume of that. I did it wrong. Remember that I got negative 81 over 4 pi, and the answer was 81 pi over 2. So integrating that after 30 minutes and getting it wrong, obviously, is not fun. Did anyone fix that? Yeah, see? So currently my wrong answer is the still best answer for that problem. I told you, you can be better than that if you invest some time. Still nothing? Terrible. Anyway, so that problem would be a joke to solve this, but I'm going to raise the stakes. How about if we have the same shape we had, so this is the elliptical paraboloid, but on the bottom we add the cone. This is clearly a model for UFO, except those are much wider, right? They look like this, and then they have a cone on the bottom, right? Exactly. Now you ruined it. Like really ice cream. It looks more like that. Unless you go to Polar Cub. If you go to Polar Cub, then it looks like this. I have no clue. Yeah, I feel every time I have to be like, you know, with a juggler in circus, like to get that thing so it doesn't fall, like melts halfway to I'm eating. I'm not complaining. It's amazing. I hope they stay open forever. What was I doing? Oh, yes, problem. So let's have some equations for this. The top given by z equals 12 minus x squared minus y squared. Bottom, how about we do blue? Bottom given by z equals square root of x squared plus y squared. And all of this, guys, is going to sit in a coordinate system like this. And when I shine the light on top of this UFO, it's going to give me a circular domain. So domain over here is going to be a circle, still unknown radius, but it's a circle. So at least I know that my theta limits are 0 to 2 pi. Now I need to figure out what is the equation of that circle. Well, hopefully we will understand that we're supposed to equal the two z equations, and that will give us the line of intersection where the object is fattest, right? That's the fattest spot of the object. So the equation of that line would be given by equaling out the blue and the red equation. So the orange stuff, set z's equal. We have 12 minus x squared minus y squared is equal to square root of x squared plus y squared. And now all we need to do is to solve this, right? The way to solve this is we use R. Nice. Why would you suffer and struggle with algebra when you don't have to? You convert this into polar realm by, first you factor out the minus to have x squared plus y squared equal to square root of x squared plus y squared. Guys, the formula is that r squared is equal to x squared plus y squared. So when you convert this into polar realm, all you get is 12 minus r squared is equal to r. X squared plus y squared is r squared, and the square root kills the square. So move all of the things on the one side. You have your r squared plus r minus 12 equal to 0. When you factor this, you get r plus 4, r minus 3 equals to 0. So radius is either negative 4 or radius is 3. 3, good. Because radius is length, and lengths are always positive. So r equals 3. So we learned that this is radius 3. Because down there. And now I can finally set up my integral. Volume is the triple integral. Nothing in here because we are dealing with volume. We have dz, r, dr, d theta. We said we want the entire shape all around, so that's 0 to 2 pi. Now the radius is the full circle, no holes, nothing, so that's 0 to 3. And now our z's. Z's needs to be converted into the polar. So the red z, right? So we have the conversion now. Red z, we already know it's 12 minus r squared, and the blue z is just r. So on the bottom of the shape, we have r, that's the blue one, and on top of the shape we have the cone 12, not the cone, the elliptical paraboloid, 12 minus r squared. Ta-da! I need that button. So now, integral 0, 0, 2 pi, and 3. Integrate out z. So that's just going to be 12 minus r squared minus r times r dr d theta. So when you integrate z, you're integrating 1. So you just get z, which is the top limit minus the bottom limit, which is what I have. You work out that algebra. Multiply by r. We get 12r minus r cubed minus r squared dr d theta, which is 0 to 2 pi. This is going to be 6r squared minus 1/4 r to the 4th minus 1/3 r cubed from 0 to 3 d theta. 0 to 2 pi. Plug in 3. So that's 3 squared, 9 times 6, 54. Minus 3, that's 81 over 4. 1, 3 dies, so this is just 9. 0 kills it all. D theta. So this is 0 to 2 pi. I have 54 minus 9 is 45. So that's 180 over 4, so 99 over 4. D theta, which is equal to 99 pi over 2. Let's say that's good, and move on. That's good? Thank you. So what was the only thing, well, first off, the orange thing, right? The orange thing was there to figure out the domain, because domain is whatever shadow is casted when you take the light and shine it above the object. So in this case, it was a circle. To find the equation of that circle is when the z from the top shape meets the z from the bottom shape, and that was given by the equation. Now, the way to solve this equation here would be to actually square both sides. If we didn't have the polar coordinates, you square both sides to kill the square root. Squaring this is going to give you 9 terms. Good luck with that. And then you bring these to the other side. Then you try to factor stuff. I mean, it will work out after 30 minutes of intense labor. You will get still, -4 and 3 at the end. But it will be a lot of work. So polar coordinates make that into a joke by simply replacing the unit of x squared plus y squared with r squared, and the entire equation immediately collapses to this, because that's your r squared, -r squared, and then that's r squared, square root kills the square, so it's just r. And then from there is a walk in the park. Do not forget to convert your z limits in the polar coordinates. So in the definition, you have these r cosine, right? In our case, as you can see, that worked out to be just 12 minus r squared. Because technically what this says is that the functions need to be in terms of theta and r. Well, it worked out to be just r and 12 minus r squared. Perfect. So that's cylindrical coordinates. That's the straight up upgrade to what we have for polar coordinates. Let's open the gates of hell. Spherical coordinates. we work with two angular measurements, so we still have good old theta that works in the plane, xy plane of the sphere. Yeah. So my domain is a circle. And this domain has the radius now labeled as rho, and it has angle theta, whether I want the full ball, the quarter of the ball, right, depends on what I want. So now I have the polar coordinates base. It's rho theta. Used to be r theta, now it's rho theta. On top of that one, I also introduced the angle phi. Now phi measures the same way the bearings measure in your Pre-Calc 2 course. If you remember bearings in Pre-Calc 2, you had your north, your south, your west, and your east. And when you have an angle, you measure it due north. So you would say north 30 degrees east. So the entire trigonometry course you had was measuring angles from the positive x-axis. And we still measure the angles from the positive x-axis on our domain, because that's theta, that's polar coordinates, and nothing is changed. However, the angle phi follows the same idea as bearings. And bearings measure everything from north. So you go north 30 degrees east or 30 degrees west, right? So that's the way the bearings work. The same deal for angle phi. It measures the z, positive z-axis, and then how much you fall one way, how much you fall the other way, away from the z-axis. So what I can do is I can take a ball and I can carve a conical shape to the center, which would have the sphere roundness on top, and calculate the volume of that thing like this with spherical coordinates, which would convert into hours in rectangular coordinates. So the way it works is when you, so this is what you do. Let's create the ball first. I'll need this. So how do we create ball in spherical coordinates? You have a center somewhere in space. You put your center in space. Then you draw out your radius. So this is the radius rho. Here is the center of the universe, and here is the radius rho. You get that rho theta around to create a flat disk, which is your polar coordinates. And now you have something that it's like, you know what the CDs are, right? They used to carry music. Okay, good. So now you have a CD or a DVD or a Blu-ray disc, right? That's what you have. Now, you have the disc. It's round, okay? So this is a round disc. And now what you do is you take that disc and you rotate that disc pi. You see what happens when you rotate disc pi? The half of that disc traces the upper part of the ball, where the bottom part of the disc traces the bottom part of the ball. Look at the disc. So I create the radius, I spin the radius 2 pi to create disc. That's polar coordinates. So now you have a circle, you have a disc. And then all you need to do with phi is to rotate that disc pi. You rotate that disc only half of the revolution, right? Because the upper part will trace the upper part of the ball, and the bottom part traces the bottom part of the ball, and you have the full ball by rotating the disk only pi. So if I want to describe the ball, the limits would be 0 to 2 pi for theta, 0 to pi for phi, and then 0 to whatever the hell your radius is to come up with the ball. We'll do that, right? But it's just important to see how these coordinates work. So now, why do I say that cutting out the conical shape that goes whatever circle you have on the top of the ball, going conically into the edge with having the curvature of the ball on top, why is that easy? Because of the phi. You have your phi working towards the north pole of the planet Earth. You drop that pi over 6, let's say, and as your theta rotates pi over 6 2 pi around, you see how it creates the cone? And when it cuts out, the top of the cone is going to be the curvature of the sphere. Is that you don't want to calculate any volumes that involve balls, right, with rectangular coordinates, because it would be absolute disaster. I guess the internet on my tablet died, which means the OBS studio died, the stream has died, and we just, I guess, yeah. Actually, no, the internet actually no, this is network. Network is working. Internet is dead. All right, well, such is life. Okay, so now we have our point to be described as rho phi theta. Rho phi theta, and we are able to find any one of those using right. You just okay. So let's find one point so it's clear. So you have 3 pi over 6 and pi over 2, let's say. So we're going to go onto our coordinate system. X, Y, and Z. I am first going to work on the domain because I just have to do the polar thing. Now, this is a little bit confusing, guys. Your polar is the first and the last. That's where the polar stuff is. So that's polar. And polar the domain, and then we'll deal with pi over 6 later. So when you are in a polar domain, this will be 3, which is your radius 3. And then you swing that pi over 2. So this is where the point is. So this is 3 pi over 2. So you see that that is on the y-axis, right? So now I know that my point is right there, 3. Now, where is that in with z, right? So what you do is you bring this up with the construction line all the way up there. What?
You did.
Okay, so that's more interesting than the point.
Because this point's going to be sharper.
The points don't have sharp ends.
That thing's huge.
Guys, it's a small bug. Like you are.
That thing's huge.
Have you seen an elephant? Elephant is huge. And then when you see an elephant in a zoo, you go, oh, so cute. You see a little bug that it's... There you go. So stop whining. This is pi over 6. They intersect here, and this is where your point is. I'm done.
Why did you graph 3 and pi over 2?
That's the, well, you know how you have x, y, z, right? So you graph these two first, and then you bring it up in z. So xy now is replaced by r theta. So I have to find where the location of the point is in the domain, and then I bring it up straight and intersect that with the drop of the angle from the north, right? So this is technically your north for the planet, I guess, or whatever. So you have that. So if you are dealing with the x, y, z coordinates, right? You first find the location in the xy plane, then you bring it up and you say, okay, that's where it is for the z equals to 3 or whatever, right? We did the same thing here. I located where the point was in the domain first, but it's a polar, right? I wrote the domain on the side. I can also write the domain for xy on the side like this and say, okay, go 5 units this way and 2 units up, and that's where it is for xy, and then bring that back, say that's your 5, 2, and then go 3 units up to get 5, 2, 3 for the point. So I deal with the domain first to find where the first two coordinates are. So now with the spherical coordinates, it's built upon the polar coordinates. So you would do the domain in the polar coordinates to find where the xy point is, and then you bring it up with the z when you drop the angle down. So most mistakes on exams and things like that happen when you measure the angle pi over 6 wrong. You have to measure that angle from the north. So from the z-axis, you get to drop it any way you need to drop it, right? Now this causes a problem, guys. We do not get a straight shot of conversion formulas, right? Like you have for cylindrical and polar. Spherical coordinates are tricky because this angle phi gets to drop in any direction that is governed by the domain. So we cannot have a set of formulas and say here's a conversion. You actually have to sit down and work out trig and angles and things every single time. It's like a chain rule in Calc 3. You actually have to go and look at the triangle you get, and here's a triangle right there. I don't want to ruin it now, but actually what I'm going to do is this. Here's your triangle, right? And you have the triangle with the right angle right there. So you have a triangle, you have the right angle, you know that this side is 3, you know that this angle is pi over 6, so this angle over here better be pi over 3, right? You also know that this is the same radius because it's spherical coordinates, so this is 3 as well. And now you can do law of cosines to figure out how tall this is, right? So there are ways to write, because you need your z. So law of cosines helps you there because you have two sides and the angle included. Right? You didn't do law of cosines for nothing in pre-calc 2. So conversion between systems now becomes harder. Conversion becomes harder, but then it's not impossible. All right, so let's take a look at the integral and describe the way the integral works. The string for this one is long. The string will be sine phi rho squared d rho d phi d theta. So that's the string. I just need to find where it is. There it is. Okay, so the integral now, again, napkin time, right? If nothing, just learn it to troll others. That's, phi rho phi theta dv. Again, we see it's a 4d, right? Because you have a function times dv. And now we have our triple integral over here. The triple integral alpha and beta Actually, let me write everything else first, and then. So we have f of rho phi theta, rho squared sine phi d rho d phi d theta. D rho d phi d theta. There we go. Now, polar is rho and theta. So theta goes from alpha to beta. If you want the full shape, 0 to 2 pi, half of the shape, 0 to pi, and so on. And then we have phi. Phi is the, again, angle. They use A and B in the book. I hate it because we generally use Greek letters. So they should be using gamma and delta or whatever other, but they're using A and B. So I'll use A and B because, you know, notation should be the same as in the book, but they shouldn't, you know, it's angles, so you shouldn't be using A and B. And finally, we have our functions, so G and H, and those should be in terms of phi and theta. So G and H in terms of phi and theta. So this is our formula for calculating spherical integrals. If you have function inside, it's 4D. If you don't have a function inside, it is 3D. So if you kick this out, you will be calculating volume. Now this is the question that would pop up on the honors test. Prove the or any test, it could be your test as well. Prove the formula for volume of the ball, of the sphere, right? So prove V equals 4/3 pi r cubed. This is something that you memorized. This is something that, you know, ancient Greeks knew like 2,000 years ago. Figuring it out without calculus, using a stick and a rope. They also knew that the Earth is a ball because you use the stick and a shadow, and they were able to calculate to within the 10% accuracy the size of the planet using a stick and a shadow. So that should be your challenge, to go home and figure out how big is the planet on which you live by using a stick and a shadow. That should be your number one priority when you go home today, to figure that out. Because someone figured that out 2,000 years ago without calculus and spaceship to go and actually see it. So now we're going back to the problem. I have a sphere, and that sphere has the radius rho. So I will say that the radius rho is between 0 and r. So you want the radius to be 1, then r is 1. You want it 5, it's 5, and so on. Theta is between 0 and 2 pi because you want the entire ball. And we said that phi will be stuck between 0 and pi because half of the disk traces the upper part, half of the disk traces the bottom part. So to get the full ball, you just need to go 0 to pi on phi. So we say that the volume of the ball will be the triple integral. We do not have any function, but we do have the string, which you have to memorize. Guys, this part over here is part of every spherical integral. The function is the one that you have or do not have, depending on whether you're calculating the volume or whatever else, right? But the string is something that you are memorizing because that is the part of the integral. So that string is going to be here even though I am computing the volume. Now, you might make an argument now, well, hold on, what's happening with your dimensionality of the equation? Dimensionality of the equation is just fine. d phi and d theta do not constitute dimensions because they do not have units of length. They are units of their radians. And radian is a ratio inch divided by inch or meter divided by meter. So the formula for arc length is S equals R theta, from where theta, which is the angle, is S over R. If the arc length, S, R, and theta, if arc length is measured in meters and radius is measured in meters, they cancel. What is the unit of an angle? We call it radians, but it's not a unit. It's not a unit of length, right? So when you understand that, you see that these two, which are both units in angles in radians, do not bring dimensions to it. And also this one doesn't, because it's a sine of an angle, which is a number, like 1/2. Sine of 30 degrees is 1/2. That's not a dimension. It's a constant. So the only three, you have two dimensions here and one dimension there. There's your 3D, right? So it's volume. So don't kid yourself that you have a 6-dimensional space, you know, 2, 3, 4, 5, 6. No, right? These are not dimensions here. You have rho cubed, rho squared, right? That's 2, and then d rho, that's 3. Which makes sense. Don't you want r cubed for a sphere? Right? Here's your r squared, and here's your another r, so that's r cubed for a sphere. So it makes sense. Of course, it makes sense math, but I'll let you figure it out. The limits: theta 0 to 2 pi, phi 0 to pi, rho 0 to r. So, you know, for honors, I ask you to prove the volume of the sphere using r. For the regular Calc 3, I say calculate the volume of the sphere of the radius 5. So you don't get to put r, you get to put 5 inside. So there you go. That's the difference. All right, so what are we integrating first? We're integrating rho. If we are integrating rho first, we're integrating this thingy. Sine phi is a constant. You copy it. So copy the first two integrals. It's rho cubed over 3. Sine phi is a constant. You copy. And then you have your limits 0 to r, d phi, d theta. 0, 0, 2 pi, and pi. This becomes r cubed over 3 sine phi, d phi, d theta. Next one. You are integrating now in respect to phi. So r cubed over 3 is a constant you get to copy. So r cubed over 3, you copy. Integral of sine is a negative cosine phi, computed from 0 to pi. And we still have d theta to deal with. 0 to 2 pi, r cubed over 3. Now, we have negative cosine of pi plus cosine of 0. D theta, which further gives us integral of 0 to 2 pi r cubed over 3. Now, cosine of pi is negative 1, and the negative over there is 1, so you get 1 plus 1 in here. So you are integrating 2r cubed over 3 d theta. Well, the whole thing is a constant. So you get 2r cubed over 3 theta from 0 to 2 pi, which is clearly 4r cubed over 3 pi. Nice. People knew this more than 2,000 years ago. Also, obviously, a cool thing to leave behind as you leave places. All right. Shall we look into some of the nice calculations? The answer is yes. Spherical integrals. I am not going to solve this because I already talked about it and it's done in the book. We're going to take a look at the homework problem, but here is the one. Oh, it's pi over 6. Great. Remember when I did this, right, for pi over 6? So you see that it cuts out this shape. And you have the curvature of the sphere on top, and you have the conical thing, right? So the curvature on top will depend on, right, and how big this cone is, depends on the radius of the sphere. And how wide the cone is depends on the pi over 6, which is how far out you want, right? You can make your cone really wide by using a large angle phi and drop it all the way down, right? Now, obviously, that would take a lot of ice cream, so they would not put cones like that, right? Which is why I eat my ice cream at home, on the plate, not from the, little cone thing. Let's take a look at problems. Here are your cylindrical problems. You can see cylinders and cones. They are great for cylindrical. And then we see these shapes, right, which are good for spherical. Now, they also give you the picture. This is a learning experience. They give you the picture, they give you the integral, and they show you the ways to deal with this. If you take a look at problem 42, do you see that it has the flat top? It's not curved. Do you see that? What is the equation of the plane z equals 4 in spherical coordinates? Well, you just look at the integral and you see it right there, right? 4 secant 5. Good luck. I know, right? It's awesome. Oh, you have a flat bottom at 2? Yeah, 2 secant 5, right there. This is why you should once in a while open the book and look at it. I can't teach every single thing because you're now in Calc 3 and there is 5,000 things. So you have to do as many of these as you can and figure out things. So now you just found out that plane in spherical coordinates, I don't see you writing these things, and then you will be complaining later. So the plane in the equals to, let's say, z equals to c, right? Z equals to c is given by c secant phi. Good, c secant phi. Why? Because we can. You see, this is some kind of cone that's not a cone because the sphere came in and just like caved it in, right? You can make a hat out of that, right? Take this, right? It used to be called a crown. Just put the jewels around and then you're very important, right? All kinds of different intersections. It is all always far away minus the close by. Far away on top, close by on the bottom if you're doing the integral. If you're placing those inside the integral, far away minus the close by. How do you measure what's far away? You anchor the R in 0, 0 in the center and then shoot the ray out. The furthest away, what it touches, that's the far away, and the closer shape is close by. That should be clear. So, when you have shapes like this, depending on what you need, right, you start from here, and you say, okay, it goes this way, the ray goes this way, so it is touching this, oh no, sorry, it's the one shape. What do I need here? The solid outside of the cone, and inside the sphere. So we need the orange stuff. So the cone is on top, the sphere is on the bottom. There we go. What would it look like? It would look like a really weird cereal bowl. If you look at the cereal bowl from the side, it will look like half of the bowl. Great. Right? So you would expect to see half of the bowl inside. But no, when you look inside, you see a conical, right? With a sharp point on the bottom, right? Through which milk will actually drain, because the 0, point right there, it's a hole, actually, right? But anyway, it would look like a sphere from like half of the sphere, half of the ball on the outside, and on the and flat on top, right? Cut, and then on the bottom, right? When you look inside, it would be a conical shape. So there will be a lot of material. The edge would be so sharp. Anytime you pick it up, it will cut yourself, right? Which gives me an idea. We should actually produce that. There's your entrepreneurial idea. Cereal bowl that leaks and cuts you every time you pick it up. Right? You can't pass that out. You can't pass on it right in the commercial. It pretty much sounds like anything else that's on infomercials. I don't know if you watch those things. Or drugs, right, when they sell. Like, take this, you'll be happy. And also, you will continuously bleed from the left eye for the rest of your life. Something like that. That's the side effect. All right. We can. The problem is that all of these problems are already set and done, so we just get to discuss them. I don't know what to say. Problem 44 is awesome because you have two shapes. You have a cone and you have a sphere, and they're intersecting and creating the shape. And you also have a flat plane, so that problem has everything going for it. I'm very happy with the problem. So let's take a look at problem 44. Now, unfortunately, it's completely solved. The only thing they want you to do is to actually integrate, which you should be able to do in your sleep. So what I have a flat plane, a disk on top, and then a cone going down, and then a sphere which cut in the bottom. This is terribly disproportionate, but such is life. The top over here is at 2, and the top of this is at 1. So you see how badly this is wrong. There's your x, there's your y, and there's your z. And now we would like to know more of this. This is terrible. It bothers me how bad this is. So from scratch. I should have first done the construction line. So let's do this orange and then erase it. So we call this a 45. So this is phi equals 45 degrees. 45 degrees, pi over 4. Professional, all right? Then I'm going to say half of 2 is 1. So let's cut it here. Erase the construction lines. Connect the cone. And then scoop out the sphere inside. This is where 1 is. Yay. Whew. Shadow is a circle on the bottom. We see the flat plane on top. Let's do that blue. Flat plane on top is rho equals 2 secant phi. We also see another row on the bottom. Let's go green. That's rho equals to 1. That's a sphere of radius 1, for those of you that are still struggling with this. So this is sphere radius equal to 1. Great. I have phi equals to 4, and I want the see, I'm using now the orange over here and orange over here. I'm going to switch this orange to red. So phi equals pi over 4, so that the orange over here would tell me that my theta is 0 to 2 pi, because it's the full thing. There we go. Nice. So now if I want to set up my triple integral for spherical coordinates, they are actually asking you to compute rho to the negative 3. Then we have our rho square sine phi d rho d phi d theta. Theta, that's my orange, 0 to 2 pi. Then we have phi. Phi is my red. Red is phi is 0 along the z-axis, and phi is pi over 4. Right, so those are the red lines. So 0 to pi over 4 on phi, that creates the cone. And now I need to have the sphere on the bottom, so that's 1. And I need to have my flat surface on top, which is 2 secant phi on top. It's color-coded. I have to post this immediately after the class, because you guys have to go and decipher all of these colors and see what goes in which limit, because, you know, all you're getting on the exam is black on white, one equation, and then, you know, good luck. So now I have triple integral 0, 0, 1, 2 pi, pi over 4, 2 secant phi. Over here I have rho to the negative 1, sine phi, d rho, d phi, d theta. So now we integrate the first one out. So when you integrate 1 over rho, what do you get? What's integral of 1 over rho? Thank you for being mentally present. ln rho from 1 to 2 secant phi sine phi d phi d theta. Ooh, this is going to be ln of secant phi. Who's excited? That's what I thought. 0 to 2 pi, 0 to pi over 4. We have ln of 2 secant phi minus ln of 1, which is 0, times sine phi d phi d theta. This is another napkin problem. 0 to 2 pi, and let's do one more over here. Guys, I have ln, so this is multiplication inside, right? If it's multiplication inside, I can write it as ln 2 plus ln secant phi. All of that times sine phi d phi d theta. Bueno? Now, for those of you that don't remember logs and things, here is some orange. ln of 1 over cosine phi is going to be the same as ln of cosine phi raised to the -1. The -1 goes in front because exponents can be pushed in front for logs. So this is minus ln of a cosine phi. At which point you go, yay, because you get u sub. You have a ln of cosine phi times sine phi. So u equals cosine. You have the sine for du. And now we have, for the first time, a non-basic integral. It's a calc 1 u sub. Ooh. So let's write this one more time now. This is integral 0 to 2 pi, integral 0 to pi over 4. Inside I have ln 2 minus ln of cosine phi. All of that times sine phi, d phi, d theta. This sine phi distributes over both of these. So I actually have ln 2 sine phi minus ln cosine phi times sine phi, everything d phi, d theta. Can you hear the silence in the room? Who would know? I just need a triple integral, right? In spherical coordinates. Attention is like at 197%. 2 pi. No, I don't need the inner integral. We're integrating now. Integral of sine phi. ln2 is a constant. Integral of sine is negative cosine phi. Minus, here comes the u sub. U equals cosine phi. Du is equal to negative sine phi d phi. So with the minus, that will make this into a plus. And we have the integral of ln of u du, all of that d theta. The limits over here are 0 to pi over 4. The limits here change from cosine phi 0, which is 1, to cosine of pi over 4, which is root 2 over 2. Nice. 0 to 2 pi. Negative ln 2. In parentheses I have root 2 over 2 minus 1. Plus. Ooh, what's the integral of ln of u? Uh-huh. No, it's not secant and it's not trig. It is u ln u minus u. You don't remember that? Let's go and take a look. We jump ship to Calculus 2. Hello and welcome back to Calculus 2 Integration by Parts, where we calculate the integral of ln, oh, that's x ln x. There we go. Hi. So if you don't remember this one, you just do the quick integration by parts on the side. It was an amazing problem. I mean, you know why is this happening? Spherical coordinates. Flat plane, right? Yeah, that's what introduced that secant. We just destroyed everything, right? But that's okay. So there it is. So we are looking into u ln u minus 1. So we go back to Calculus 3. Hello and welcome back to Calculus 3. Over here we have now u ln u minus 1 computed from 1 to root 2 over 2. And all of that still needs to be integrated d theta. Oh yeah, we're not leaving till 4 today. Did I mention that? I gotta eat and then I have 4:30 class. So 4 is the limit. 0 to 2 pi. Let's see what we got over here. Well, that's it. I'm just gonna get this minus sign and make this 1 minus root 2. There we go. If I swap the order inside, then the minus dies. That's that. And then we go into, if stream died, by the way, none of this is on stream. But I still see the red circle on top, which means issues with transmitting this stuff. Plus, plug in a root 2. So that's root 2 over 2 ln root 2 over 2 minus 1 minus plug in 1. So that's 1, ln of 1 is 0, minus 1, so the whole thing is just plus 1. Nice. There we go. D theta. We still have one integral to go. I don't know about you, but this is amazing. I'm having the day of my life. So ln 2, square root of 2 over 2 ln 2, plus root 2 over 2 ln root 2 over 2, minus root 2 over 2, plus 1. There we go. D theta. Oh, by the way, all of this is a constant, so you can just leave it like that and just multiply everything by 2 pi. But where is the fun in that? Is there anything that we can cancel? Yes, because the ln 2, this one, can be written as ln root 2 minus ln 2. And then the ln root 2 is 1/2 of ln 2 minus ln 2, which becomes negative 1/2 ln 2. Beautiful. So now I have integral 0 to 2 pi, I'm not giving up, ln 2 minus root 2 over 2 ln 2. The whole term over here works out to be negative 1/2 ln 2. And then we have this minus root 2 over 2 and then plus 1, d theta. So now we factor out ln 2. And you're left with 1 minus root 2 over 2 minus 1/2 minus root 2 over 2 plus 1. And then all of that times 2 pi, and because I got bored. That's the exact solution. If you want to go in your calculator and get the decimals right to the 7th place, you can. How those spherical integrals. Now, yeah, they tend to be a little bit long to compute because, guys, it's a triple integral, obviously. So this one worked out to have u sub and by parts, so that's good. Also some ln rules and some trig rules, and then combination of those, and then yeah. Good luck. See you tomorrow.